Hello students. So basically we have understood the concept of perturbation. What does perturbation means? Perturbation means small changes in the Hamiltonian, right? And we have also seen, like we have also solved few questions in the previous lectures. So in this lecture we will solve a new question that says find the effect of finite amplitude on the period of a plane pendulum by using first order perturbation in time dependent format. Now, before starting this question, we should know a few things. Like when I consider small oscillations, a plane pendulum behaves like a harmonic oscillator. When you consider small oscillations, at that time the plane pendulum will behave like a harmonic oscillator. You already know what harmonic oscillator is. We have done the finding the Hamiltonian of harmonic oscillator in the previous chapter also, that we had done in a class, like the offline lectures. Okay, so you already know how to find the Hamiltonian of a harmonic oscillator. So what they are saying is that when you consider small oscillations, the pendulum behaves like a harmonic oscillator, and its frequency is actually independent of the amplitude. Its frequency does not depend on the amplitude, but when in case of small oscillations. But as the amplitude increases, the potential energy does not resemble with the harmonic oscillator form. Okay, the potential energy we calculate, no, that does not resemble exactly as the harmonic oscillator form. Like previously, when there are small oscillations, at that time the plane pendulum will behave like a harmonic oscillator, and obviously its frequency would be independent of the amplitude. But what happens when the amplitude increases? No, at that time the potential energy does not resemble exactly the form of the potential energy in harmonic oscillator. So frequency shows a small dependence on the amplitude. Okay, now in before, when there were small oscillations, at that time frequency was independent of the amplitude. But as the amplitude increases, at that time frequency will start depending on the amplitude. This is the thing you should know. So obviously, there would be a small difference in the potential energy, because when you will see in the previous questions also, we studied. What we did was, first we considered the unperturbated case, and afterwards we considered the perturbated case. See, I can show you also. We have already done all these things in the first question itself. We had done. No, this is my second question. No, this is my first question. See, what did we do? First, we found out the Hamiltonian in the unperturbated case. Then we considered the perturbation. See, first we found out the Hamiltonian in the perturbated case, and after that we considered delta H, that is the perturbation Hamiltonian, and then we solved further. In this question we will also do the same thing. What we will do, we will consider the unperturbated case first. In the unperturbated case means the case where we have considered small oscillation. At that time the plane pendulum will behave more or less like a harmonic oscillator. So harmonic oscillator we have already studied. So basically, no, the plane pendulum behaves like a harmonic oscillator before the perturbation, like in the unperturbated case. Fine. So we will do everything analogous to the harmonic oscillator. Okay. So see, we'll start with the question. The Hamiltonian for a plane pendulum consisting of mass point m at the end of the weightless rod, the length L is given by. So basically we have mass m, we have length L, and we know the Hamiltonian for a plane pendulum is given by this thing, p square. See, obviously in this case there are there would be two generalized, sorry, there would be two coordinates. First would be theta and the other coordinate would be p. Okay, obviously, because now we are considering oscillations. Okay, in this case there would be two coordinates. Theta would be the generalized position coordinates and p would be the momentum coordinates. When we consider linear, when we consider linear, that is a translation. At that time we consider x comma p for one dimensional, right? because because at that time there was no theta, there was no angle. Now we are considering oscillation, so the general, that is a position coordinate, would be theta. Okay, so now we have two coordinates, theta and the momentum coordinate. So this would be the Hamiltonian. H is equals to p square upon 2 ml square plus mgl in bracket 1 minus cos theta. Now obviously see, I have solved for you to make it simple. You can solve from here to here by using the uh, expansion series of cos theta. You know what cos theta is? Cos theta is 1 minus theta square upon 2 factorial plus theta to the power 4 upon 4 factorial plus theta to the power 5 6 upon 6 factorial. You can put this value over here and this one you can take here. So see what you will get. You will get this equation. After solving, you will reach here. What you have to do is you have to take theta square upon 2 common, and hence from the 4 factorial 2 will come outside of the bracket, and hence you will get in this term in the denominator 4 into 3 into 1, and in this term 6 into 5 into, since 2 has been taken common. So after solving, finally you will get the value of 1 minus cos theta. That would be this value. You have to replace this value over here. When you replace 1 minus cos theta over here, you will get this equation, that is equation number 1b. Okay, where we obviously know that the momentum conjugate to theta is denoted by pp, is the momentum coordinate. So 1b is the equation which gives us the Hamiltonian, that we have just solved the value, like we have put the value of cos theta and we have solved. But since I have told you, before perturbation, the oscillator is behaving like a, sorry, the pendulum is behaving like a harmonic oscillator. Okay, so we plus one more thing you have studied before also. In the first question we had the value of Hamiltonian. That was the case of translation. In 12th standard, you know that the mass in the translation motion, that is the mass in the translation motion, is analogous with the moment of inertia. And the like x, that is the position coordinate, over here we consider theta. In case of rotation we consider theta. So this I have written so that you can understand from where my equation 2 has come. So equation 2 has come from here, because you know analogous to mass we have moment of inertia, and analogous to position coordinate we have x, we have theta. So using this we can write this, and this is the value of Hamiltonian. Okay, which is 1 upon 2i. I is the moment of inertia of the pendulum, and omega, you know, the angular velocity, and theta is the position coordinate, that is theta. So we also know the value of I for the pendulum is given by ml square, and the value of omega square is given by mgl upon I. Okay, now since I is ml square, if you put the value of I in the denominator, mass will get cancelled and one L will also get cancelled, hence you will get g upon L, where g is the acceleration due to gravity and L is the length of the string. Mass is the mass of, m is the mass of the pendulum. Okay, all these things you already know. So even if you don't know, like you can see now, the value of I is given by ml square, and the value of omega square is given by g by L. Now we have calculated. I hope I am clear. Now since I have told you that we are now considering the unperturbated case, first we will find the value of first we will find the solution for the unperturbated case. So we know that in unperturbated case the pendulum is behaving more or less like the harmonic oscillator. Okay, so for harmonic oscillator we have already done everything. We have found the value of Hamiltonian in the previous chapters. I think in chapter number 3 we have done. So see, the Hamiltonian of a harmonic oscillator is given by this, where k is what? The spring constant. Okay, and the P and Q are the position coordinates. So we also know the value of omega, which was given by under root of q by m. So using the value of omega, we will get finally this equation. Okay, take 1 by 2m common. After getting the second equation, take 1 upon 2m common, and finally you will get the last equation, which is h is equals to 1 upon 2m p square plus m square omega square into q square. Now, since we also have studied the action variable and the phase angle, we know the action variable is denoted by J and the phase angle is denoted by B. So now we have two new canonical variables, that is W and nu. This W is given by nu t plus beta. Nu is nothing but frequency, which is given by omega upon 2 pi. So now further solving, since there is you know that there would be perturbation, okay, when we will consider uh, like the amplitudes will increase, no, at that time there would be some perturbation, and this will cause the change only in two things, that is J, that is the action variable, and beta, that is the phase angle. The perturbation will cause changes in two variables, that is J and beta, and because of the changes in J and beta there would be change in the coordinates, that is theta and p. So these would be the corresponding changes in the coordinates theta and p because of changes, because basically because of perturbation. Perturbation means change, okay. So because of perturbation, the theta and p would be this way. So I have not first just this is before perturbation, okay. So value of theta and p would be given by this. Now again, we in the bracket all this I am writing the solutions of this thing, a harmonic oscillator, because we know that before perturbation the pendulum is behaving like a harmonic oscillator. So the value of q in case of harmonic oscillator, this is the value of p, that is the position coordinate, and the momentum coordinate are given by this. So now, but we have to use the variables J and beta. So in terms of J and beta, Q and P are given like this in equation number 1 and 2. So this will give you Q and P in terms of J and beta. So basically this in this term we have finally Q and P, where we have J. Okay, q is equals to under root of j upon pi m w, sorry, omega plus sine 2 pi w. See, this w is different. W equals to, this is different, and this is omega. You should not get confused in both the quantities. In bracket, I have taken omega, and this is w. W is nothing but nu t plus beta. Okay, this is the value of q and this is the value of, that's why I'm saying that this q and p has in it j and beta. You must be thinking, where is beta? See, I have already told you the value of w, nu t plus beta. So in this there is beta, in w we have beta as well. So finally this would be the value of q and p in terms of j and beta. So solving further, in the unperturbated system, J and beta are constant. See, when you consider the unperturbated system, no, in that case, the value of the phase angle and the action variable would be constant. Okay, these values would be constant, the value of j and beta. But obviously when we consider perturbation, there would be small changes in j and beta. So up till now we have considered when there was no perturbation, we have not considered the perturbated Hamiltonian. In that case, the equation number 4a and 4b will give you theta and p, and these would be the actual solutions for the unperturbated case. Now what we are doing is we are finding the value of, no, we have written the value of delta h. This delta h is nothing but the perturbated Hamiltonian. In the previous questions we have also done the same way. First we found out the value of x, that is we found out the value of we have found out the value of this thing solution when there was no perturbation. Now we are considering perturbations, no. So in that case you have to write the perturbated Hamiltonian, which is given by delta h. Now here there is theta, and you know the value of theta from equation number 4a. We have the value of theta. So using the value of theta from equation number 4a and putting in the value of delta h, you will get this equation. After you get this equation, things will get easy because you know the value of I and you know the value of omega square. See, I have already told you, if you don't know, you should remember it now. The value of the moment of inertia is given by ml square, and the value of omega square is given by g by l. When you put these values and you solve this equation, you will reach here. It's easy, just few cancellations and all, and finally you will reach to this equation, that is minus j square upon 24 pi square ml square sine 4 2 pi nu t plus beta. This would be the value of delta h, that is the perturbated Hamiltonian. Now what you have to do is you have to find the value of beta and j, because we I have told you that when there is perturbation, before perturbation beta and j are constant, they are just constant. But when we consider the case of perturbation, there are small changes in j and beta, and these changes will cause changes in the Hamiltonian, and that will be your new delta h, that is a perturbated Hamiltonian. So when I will take beta dot, I will use this formula del j of delta j. And when I will consider j dot, we have already done this previously many times. So now you must know that the value of j dot is given by minus del beta delta h. Now in order to find the value of beta dot, you have to differentiate delta j by j partially. Okay. So this is the value of delta j when you will differentiate it with respect to j. See, all the quantities are free from j, only you have j here. So the derivative of j square is 2j. So when you will put 2j over here, this 24 and 2 will get cancelled, and you will get 12 in the denominator. And hence you will get the value, this thing, j upon all these values will get, because only there was j in this term, other terms are free from j, thus partially differentiating delta h with respect to j is quite easy. So hence you will get the value of beta dot. Now in order to find the value of j dot, you have to differentiate delta h with respect to beta. Now beta is in the sine term, right? It is in the angle of sine. So basically all this is free from beta. When you will differentiate this term, you will get 4 sine cube 2 pi nu t plus beta, and the derivative of sine is cos 2 pi nu t plus beta. And solving it is also easy, and you will get the value of j dot after taking the minus sign and taking the derivative of delta h by beta, partial differentiation. Hence you will read to this equation. Now considering beta, here there is sine to the power 4 2 pi omega t plus beta. Now what happens is, when you consider a cycle, sine to these where this value will go on changing, no? So we have to pick a particular value, so we take the average of all the values, and this value come out to be 3 by 5. And for a particular cycle, we take the average of all the values, because in a cycle the time will change and it will give you different values of this term. So hence I will take average, I will get the average as 3 by, not 5, 3 by 8. So using this value in place of this term, okay, you will get 3 by 8. Now you will solve it further, and hence you will get the value of beta dot bar, because I am taking the average value. Actual value of beta dot is this. After taking the average over here in this term for a particular cycle, since for in every point in a cycle there would be different values, we cannot put all the values, so we took out an average, and this was 3 by 8, and using this value over here, you will get the value of beta dot bar, that is minus j upon 32 pi square ml square, and this would be our equation number 8. So now what we have to do is, we have to solve further. Now finally you have got the value of beta dot bar. Now when you will integrate beta dot bar, obviously here with respect to time t, here there is no time, like all the quantities are free from time t. So after integrating it, we will get beta equals to this quantity into t plus beta naught, where beta naught is the constant of integration. But this quantity is nothing but beta dot bar from this equation. So replacing the value of this beta dot bar, you will get beta equals to beta dot bar t plus beta naught. This will give you the value of beta, okay, after the perturbation. Same you can do for j dot also, but what the trick is, when you take an average of this quantity for a particular cycle, it comes out to be 0. Hence the value of j comes out to be j dot comes out to be 0. Thus there is no change in j, and hence j shows no secular perturbation. There is no perturbation in j. Okay, and the value of beta exhibits a perturbation at a constant rate of beta dot bar. Here we have found the value of beta. This beta shows some changes in the because of perturbation, but j will show no change. Hence we have completed this question also. Since the exam is MCQ based, you have to learn all these values by heart, because you don't have to solve over there. You should know the value of the perturbated Hamiltonian in the pendulum case. In all the cases, everything you have to learn by heart. Only then you would be able to solve the questions, because you won't have enough time to solve all the questions like the theoretical questions.